Thank you so much. Yeah, warm welcome from our side. Well, it's great to be joined by so many fellow federated learning enthusiasts. I'm here with Leo. We're present from Cologne and Hamburg, and we'd like to present a case that we're doing with Siemens, actually. And fitting with the subject of today, we will dive into the industry more specifically with Siemens and their printed circuit board production globally. Now, our mission at Katulu is to get federated learning out of the lab and into production, where it generates value for our customers. So get ready to drop your lab coats with us, and let's dive in. So when it comes to manufacturing, Siemens' first and foremost concern is to live up to customer expectations when it comes to quality. So no matter where in the world, they want to deliver perfect products to their customers, the printed circuit boards, where they have a large variety. And the team that we're working with, their job is to make daily life in the factories easy for the workforce, and to also continuously optimize the quality control of production. This is measured by first pass yield, which is a metric to measure the effectiveness and quality of manufacturing processes, meaning in an ideal world, we will detect defects immediately. And this is not the case today in modern international manufacturing footprints. So Siemens decided, in order to optimize quality, to revert to federated learning in order to protect their own trade secrets, meaning everything that is happening within the factory should stay within the internal Siemens factories. It should also be more a sustainable approach to using machine learning on the shop floor, because with 1 terabyte of data harvested per production line per hour, not everything can be sent to the cloud. And then, of course, there's regulatory compliance as well, which in electronics manufacturing is a major concern. A lot of data, the data cannot travel across country borders. So in order to optimize those production processes around the world, they decided to train locally and use federated learning to make it happen. However, if we're looking at their global manufacturing footprint, what at first sight looks like a pretty easy task, when you start diving a little bit deeper, you can actually see that this heterogeneous setup is actually a uniqueness nightmare. So instead of having a factory that resembles every other factory in the world, we actually have factories that are unique. And when we look at all this heterogeneous data, so our task was to really make sure that with this setup that Siemens has today, so 1,000 and plus product variations, more than 100 models that are being trained locally all around the world, more than 60 production lines, and hardware that also varies across the globe. How can we help Siemens scale this from one facility to all production facilities worldwide? And I'm really happy that Leo is here with us today, and he's going to reveal the secret to how to scale federated learning in production.
Thank you very much, Anna, for the introduction. Yeah, I'm Leonhard. I'm from around Cologne today, and I will talk about how we can scale up federated learning for Siemens. And before we do that, I would likely quickly go back and look at this current state of the art, what we do with federated learning and how we usually use it in the lab. So we have a factory with some machine. In the Siemens use case, we have a PCB production line, and then we invent some data processes like an ETL pipeline and a model that is then installed close to the machine, basically as a client as we know it, and then connected to our federated learning server. And somewhere else in Germany or in the world, we have something similar. And then we do federated learning by training locally, sending updates to our federated learning server, do some form of federated averaging or something similar, and then we send it back to the clients that run on the local ground close to the machine, and we can continue and get our models trained on that kind of scale. But what is going to happen if we want to change something within the process? So for example, they need to resemble a process line, or they get an extra sensor and they would like to introduce that kind of data into their pipeline and into their model. Then we need to go back and change all the code on our clients, reinstall them basically. And this is a lot of manual work. So that is one of the hardest problems that we were facing when working with such a large corporation and such a diverse set of factories. And what we try to do there, or what we are doing, is we basically decouple the process of data acquisition and processing from the problem. Basically, what we want to solve, increase the quality inspection, or basically decrease the wasted products in the end. So how do we achieve that? We take a step back. Instead of using a client, we now call it an agent, what is running on the factory side, because it basically doesn't know anything about a problem. There we come in as a data scientist or as data scientists and think about, okay, what kind of data do we need? And what transformation do we need to apply? And what kind of model do we like to do? And that's something we use our usual tools like NumPy, Pandas, Torch, and we can define a workload with that. So basically, from a Python script, we can then define what is going to be run on the agents. And before going deeper into the process, I'd like to give you a short demo on how this looks like in code and what actually happens when this is going to run. So what I show you here is basically a side-by-side view of the same script. And I'll try to quickly walk you through that and then show you what is going to happen if I run that script. So what you see as the first step, what we do on the left is we connect to a federated learning server and get a data source. If you want to know why we do that, we can have a longer discussion about that. For the short answer, it's just to basically decouple process and problem. Then we need to select what kind of feature we would like from our data set, basically like we would do with Pandas, and a target that we are trained for. Then we need to define a pipeline for inputs and targets, basically for our features and for the target we train for. This example here is for internet data, so basically IP data that was collected, and we try to label them as good or bad. And this is just the ETL pipeline that we basically need to define on the right side. Now moving to the model that we use, it's a simple sequential torch model. And now comes the interesting part. What we do to start federated learning with that kind of solution, we build a workload that includes the data pipeline, which is here highlighted as inputs and targets. And we compile our model such that we can send it to the clients or to the agents and run it there. And of course, we need to provide some metadata like what kind of optimizer to use, what's our loss function, what's the best batch size, and how many rounds do we need to train. For this simple example, it's just 5 rounds so that we can see results very fast. And what you see in the terminals down here, we have a server running in the left terminal. Then we have 2 agents connected. And now we basically perform the data science job to run this workbook, which defines what we would like to run on the agents. And if we start that, it will take some short time for the agents to register with the server, which we now see the first one completed, second one completed, and now performing the workbook, we see that the agents give some kind of information on the task, not too much, but for debug purposes, it's enough. And now it already finished, and we can get results back on the metrics, how good our model performed. So that's just to give you an idea how it looks like from the data science perspective, or how the feel is to work with it. And to go a bit more into detail, what is going to happen in the background from what you saw, let's jump back where we left off in the presentation. So we defined the data pipeline and the model, which is sent to the Federated Learning server that distributes that to our agents. And now we end up basically in a similar situation as we started off. We can now just perform Federated Learning. We send the locally trained weights, do an averaging, and return them to the agents. And now we're solve Federated Learning, but in a bit more flexible way. And this needed to basically enable Federated Learning for a large company like Siemens, where we have many factories worldwide. We have a local or a global Federated Learning server that is connected to all the factories where we have the agents running. And we only have at a central location a data scientist who can now work with the data from all factories by defining workloads that are then sent to specific factories. And there are some rules how you can decide which factory should be used and which not. And through that flexibility, we can send different type of pipelines and models to either same factories again or different factories. And what this helps us is to enable large-scale federated learning operations with low maintenance. We only need to install an agent once and then can run many data pipelines and train different models. We are flexible with our pipelines, and we can exchange models whenever we have changes in the data or we see that the model is not performing as we would like it to be. So it's easy to develop new models, and it's familiar to all the data science tools we basically use every day as data scientists. And where's the benefit for Siemens? So they have a predictive quality at early stage, so they don't need to waste the whole product process to do quality inspection at the end. They can train an AI model using federated learning to predict at the early stages possible the quality of their product, which will help them to reduce waste, because at some stages they could recycle parts from the PCB. And this will help them to give them cost efficiency and solve some more problems. And whenever you're interested in trying out how the platform we develop works, or you want to try it yourself, or want to get in touch with us to learn more about how we solve that problem, or what's all included in there, we're looking forward to meet with you. And whenever you have a question, and otherwise you can go to our website, katulu.io, and sign up for a free use of our platform. Thank you for your time. And
thank you so much. That was a great talk. We have time for a couple of questions. So any questions in the audience or online? We've got one online.
So Nasron asks, custom models pipelines are custom code. This is usually a security risk. Running it on site, what are the controls in place for that?
Yeah, basically, it's correct. It would be custom code, but what we do is we basically provide a sandboxed version of the tools we can use. Like, we control the type of operations you can do for your data pipeline and for your model. So we can control that you don't send any kind of data we don't want you to send to anyone else, or store data on a hard drive or whatever. So it basically is in such a way that you can only perform operations without any security issues, but still provide you the full flexibility to perform everything you need for federated learning.
I see. Sounds good. Other questions? Yeah, there's another one from online. It's great to use the online questions.
So the question is also from Restaurant. Usually as part of the data science process, there's some EDA required to expose some information about the data. How do you avoid extracting the data from the factory sites as part of the workload? For example, can I run a workload with a pipeline that extracts, centralizes all data?
Yeah, I think I already touched on that question in the previous answer, but I can just emphasize, with that pipeline, you're not able to extract any data from an agent and send it to the server. That's very limited, basically, to wait updates. So you can't really extract anything. You don't lose security with using that. You just gain more flexibility. And sure, if you want to know more about that, how we solve that and what are possible limitations in there, or what are improvements to current process, we are happy if you reach out to us and we can have an in-depth discussion, which I think would now give us a lot of overtime if we start to do that now.
Okay, great. Well, thank you again.
Thank you.